Unit 8, Chemical Bonding, pages 171 to 176, Ionic and Covalent Bonds. Ionic bonding. Ionic bonding results from a positive and negative electrostatic forces. Electrons are transferred to and from the atoms, making them ionic. The oppositely charged ions stick together to make ionic compounds. So you have someone who loses electrons, which becomes a positive charge, and then another atom that gains electrons and becomes negative. And then the positive and negative are going to hold the molecule together as electrostatic forces. Ionic bonding results from positive and negative electrostatic forces. Electrons are transferred to and from the atoms, making them ionic. The oppositely charged ions stick together to make ionic compounds. For example, sodium gives up one electron to achieve a filled shell electron configuration like neon and gets a positive 1 charge. The chlorine accepts one electron to achieve a filled shell electron configuration like argon and becomes a negative 1 charge. The ions are held together in an ionic bond that results from the electrostatic force between the opposing charges. When do ionic bonds form? When the difference between the electronegativity of the two atoms is large, ionic bonds will tend to form. If the difference in electronegativity is greater than 2.0, the bond is probably ionic. We're going to look at covalent bonding as well. This usually means the atoms are metals reacting with nonmetals. For example, here's sodium, which is a metal. Here's fluorine, which is a nonmetal. And then the electronegativity difference between them is a total of 3.1 because fluorine is 4.0 and sodium is a 0.9. And so you subtract them and you get a difference of 3.1. Since that difference is greater than 2.0, this is considered an ionic bond between sodium and fluorine. Covalent bonding results from a sharing of electrons, not a transfer of electrons like an ionic. So here you can see the 1s atomic orbitals of two different hydrogens, and they actually overlap and share space, and then the electrons actually will spend their time in this space at a high probability. Covalent bonding results from the overlap of half-filled atomic orbitals. It is not easy to explain why this sharing of electron results in a bond. The bond is a purely quantum mechanical effect arising from the physics of small particles. These effects are sometimes difficult to explain in the macroscopic physics that we understand from daily experience. Note that the hydrogen atoms in the figure are both exactly the same. The electronegativity is the same. So electrons are shared rather than being transferred from one atom to another. Why does covalent bonding occur? Covalent bonding occurs when the difference in electronegativity between the two atoms in the bond is less than 2.0. This typically happens when bonds are formed between two nonmetal atoms. For example, nitrogen and oxygen are both nonmetals. Nitrogen has an electronegativity of 3.0 and oxygen has a 3.5. The difference between these is 0.5. The type of bond that occurs with a small electronegativity difference of 0.5 is classified as polar covalent. Metallic bonds. Bonding between metal atoms is called metallic bonding. Orbitals from many metal atoms overlap, which allow electrons to migrate from one atom to another atom. This gives rise to the high conductivity observed for metals. Polar bonds. When the electronegativity of two atoms in a bond is different, the electrons will be more strongly pulled toward the atom with the higher electronegativity. So here you have hydrogen and you have fluorine. Hydrogen's electronegativity is 2.1 and fluorine is 4.0. Because 4.0 is a greater electronegativity, the electrons are going to be pulled towards the fluorine, causing an unequal distribution of charge. You're going to have a partial negative charge on the fluorine and a partial positive charge on the hydrogen. And this is called a dipole. And so you'll notice that we have a pull towards the fluorine, so there is a dipole going towards the fluorine atom. We say the HF bond is polar because the shape of the molecular orbital is skewed towards the atom with the higher electronegativity, fluorine in this case. This creates a partial negative charge on the fluorine and a partial positive charge on the hydrogen. The partial charges are indicated by this lowercase delta symbol. As the difference in electronegativity, change in electronegativity, becomes larger, the bond becomes more polar. As a general rule, when the difference in electronegativity is equal to 0 and up or less than 0.4, the bond is nonpolar covalent with an equal sharing of electrons. If you have a difference that's greater than 0.4 but less than 2.0, then it's considered a polar covalent bond. And if you have a difference that's greater than or equal to 2.0, then the bond is considered ionic. So here are some examples of different bonds, and you can see these are two different elements, and the difference in their electronegativities is 0.9, which falls in the range of 0.4 to 2.0, and so this is a polar covalent bond. Notice that Br2 is two identical atoms. Automatically, you're going to have a 0 difference in electronegativity, which is going to be a nonpolar covalent bond, and that's up here. Carbon and oxygen has a difference of 1.0, which falls in this range here, which makes it a polar covalent bond. Carbon and hydrogen have a 0.4, and so because it is equal to 0.4, it's going to be considered a nonpolar covalent bond. Sodium and hydrogen have a difference of 1.1, which falls in this range, and that makes it polar covalent. Even though it's a metal and a nonmetal, they have electronegativity values that are too close to one another to be ionic. And then sodium and chlorine have a difference of 2.1, which is going to fall in this range, and that's going to make it ionic. So for HCl, the difference in electronegativity can be calculated by subtracting the values listed for each of the elements in the table that was on the previous page, and we're going to get a difference of 0.9. The chlorine atom has the higher electronegativity compared to hydrogen. This tells us that the chlorine atom pulls more strongly on the electrons in the bond, giving the chlorine atom a partial negative charge and the hydrogen atom a partial positive charge. The difference in electronegativity equals 0.9 indicates that the bond is polar covalent. And anytime it's polar covalent, then one of them is going to be partially positive and one of them is going to be partially negative. Here's the diagram to illustrate that point where the chlorine is partially negative and the hydrogen is partially positive. This means there is a dipole pulling towards the chlorine and away from the hydrogen. In the carbon and oxygen molecule, the difference in electronegativity is 1.0, which also falls in the polar covalent range. The oxygen atom has the higher electronegativity compared to the carbon, and so the oxygen has a partial negative charge, and the carbon has the partial positive charge. The electrons are more strongly pulled toward the oxygen, which creates a dipole towards the oxygen. Here's your note card for this section. The change in electronegativity can be used to determine the bond types by subtracting the respective electronegativity values. If you have an electronegativity that falls between 0 and is equal to 0.4, then it's going to be nonpolar covalent, which means there's an equal sharing of electrons and there are no charges present. If you have a difference in electronegativity that's greater than 0.4 but less than 2.0, then it's polar covalent, which is an unequal sharing of electrons, and so there'll be a partial positive on the less electronegative atom and a partial negative on the more electronegative atom. If you have a difference that's greater than or equal to 2.0, then it's going to be ionic, which is a transfer of electrons, which results in a positive charge on the metal and a negative charge on the nonmetal.